We are starting Unit 7 today, which is on area and volume, which will be review from last semester. We're also going to talk about polar curves, area of polar curves, as well as surface area of 3D rotated solids. So we're going to start with something that you're probably very familiar with, which is the area between two curves. So remember that what we are essentially doing is taking a Riemann sum, just the way a regular volume or area curve would. But what we're doing is our rectangles, we're going to have to consider the whole rectangle underneath the top curve. And then we want to subtract the rectangle underneath the bottom curve. That's going to leave us with just the area that is between the two curves, okay? So the integral is going to be the integral from a to b of f of x minus g of x. That's getting this height of the rectangle right here. You can also do this sideways. If I had a curve maybe that looked like this and like this, I could do horizontal rectangles. And if that's the case, we would do the rightmost curve minus the leftmost curve. And you would integrate with respect to y. But otherwise, the process is exactly the same. Okay. Number 1 says, if R is the region bounded above by the graph of f of x and below by the function g of x over the interval from 1 to 4, find the area of region R. So it was very kind of them to tell us which one was the top and which one was the bottom. If we don't know, then we need to look at the graphs. Typically on the AP exam, these types of questions, the graph is provided. So what we need to do is the integral from 1 to 4 of f of x minus g of x dx. So for this problem, that's going to be 1 to 4 of x minus 4 minus 3 minus x over 2 dx. Notice the use of parentheses here. It does matter because we need to make sure that we distribute that negative. So if we do a little bit of simplifying here, we can go ahead and distribute this negative. I'm going to also think of this as 2x over 2 so that I can get a common denominator. So that gives me the integral from 1 to 4 of, this is going to be 3x over 2 minus 7 dx. So this will become, we're going to go ahead and do the antiderivative now. So it'll be 3x squared over 4 minus 7x. And we need to evaluate that from 1 to 4. Remember, using our fundamental theorem of calculus, we're going to do f of b minus f of a. So the first one, if I plug in 4, I'm going to get 12 minus 28 minus, if I plug in 1, I'm going to get 3/4 minus 7, which is 28/4. I'm going to go ahead and call it that way. And we get negative 16. Inside here, we get minus negative, so it'll be plus 25 over 4. 16 is 64 over 4. So when we add that together, I believe we get negative 39 over 4. Let me double check that with my calculator. And that is what I'm getting with my calculator. So there we are. All right, number 2 says, let R be the region bounded by the graphs of the functions f of x equals 9 minus x squared or x over 2 squared, and g of x equals 6 minus x. Okay, we want to find the area of the region. Now, these you could probably come up with a sketch of a graph on your own, but it's all right for this one to go ahead and sketch this in your calculator just for the sake of time. So when I look at my calculator, I see something like this. And so it doesn't give us an interval. It says find the region bounded by these graphs. Well, if you see, we have 2 points of intersection that create this bounded region right here. And so in that instance, we know that our integral needs to go, the parabola is f of x, so that's the top, and g of x is the line dx. Now the question is, what should our limits of integration be? And so in order to figure this out, we need to find the 2 points of intersection. And so these equations are not too bad to do by hand. This is going to be 9 minus x squared over 4 equals 6 minus x. I'm going to go ahead and multiply everything through by 4. So I get rid of that fraction. And we could go ahead, let's rearrange this first. X squared over 4 plus x plus 3 equals 0. Now if I multiply through by, I'm actually going to do -4 so that I make my first term positive. So that'll give me x squared minus 4x minus 12. That does factor to x minus 6 and x plus 2. So the two x values are positive 6 and -2, which looks about right based on the graph that we are looking at. And you can see that in your calculator pretty accurately. So that's what we're going to use for our limits of integration is -2 to 6. And so I'm relatively confident that you could integrate these yourself. So we're not going to spend a lot of time on that today, but the answer that you should get is 64 thirds is what I get when we do that integral. I just put it in my calculator for now, but remember, you do need to know how to do the integral by hand on ones like this. Okay, so what to take away from this one is needing to find those points of intersection. When they don't give you an interval and they tell you that the region is bounded, you're looking for an enclosed bounded space created by the intersection of the two graphs. Okay. Number 3 is very similar. So we want the graphs of sine of x and cosine of x from 0 to pi. So this is one that you should be able to come up with the graph without a calculator. So let's go ahead and sketch this. So I'm going to say pi halves, and I made that pretty small. Let's space these out a little bit better. Pi halves and pi. So the sine graph, f of x, remember sine starts at 1. So here's 1, here's -1. The sine graph starts at +1, and then it goes to 0, and then it goes to -1, and then it'll go back to 0 eventually. So the sine curve looks something like this. And then the cosine curve is very similar, but it starts at 0. Oops. Starts at 0 and goes to +1, and then back to 0, and then down to -1. So this graph looks something like this. Okay. We want to find the region from 0 to pi. Now, here's the weird thing that happens in this case. From 0 to somewhere right there where they intersect, we have a bounded region. And then from that same value over to pi, we have a different bounded region. Notice that the, now let's remember which one is which. This one is g of x. So for the second half, g of x is on the top. And for the first half, f of x is on the top. So the first thing we need to do is figure out where this point of intersection is. So we need to know, where does sine of x equal cosine of x? Hopefully you know that that happens at pi fourths and beyond, but clearly the one we're looking for right here is pi fourths because that's between 0 and pi halves. All right, so we have to set up two different integrals in this case. We want the integral from 0 to pi fourths of f of x minus g of x dx plus the integral from pi fourths to pi of the, because of the way these oscillate in different directions, now g of x is the top equation and f of x is the bottom of the equation for the rest of that, okay? So this one should be pretty easy for us to do without a calculator. F of x is sine of x, so that's going to be negative cosine of x. And then g of x is cosine of x, so that's going to be minus sine of x. When we do our antiderivatives, we want that from 0 to pi fourths, plus this next time is going to be sine of x minus negative cosine of x, so it ends up being plus. We want that one from pi fourths to pi. So pi fourths is a pretty easy one to do. So first we're going to get negative square root of 2 over 2 minus square root of 2 over 2 minus negative cosine of 0, which is going to be negative 1, minus sine of 0, which is 0. That's our FTC for the first integral. Now the second one, we want, oops, I don't need that. The sine of pi, which is also 0, plus the cosine of pi, which is 1, minus the sine of the square root of, or sine of pi fourths, which is square root of 2 over 2, plus the cosine of pi fourths, which is also square root of 2 over 2. So here we get negative 2 root 2 over 2, so that's going to be negative square root of 2, plus 1 minus 2 root 2 over 2, which is just square root of 2. So we end up with 2 minus 2 root 2 for our area. I would say that that one is certainly a possibility for a no calculator question. Okay, here is another example where we might need two integrals, or we can think of looking at this in a different way. So we want the region that is shaded in there. So that's just the area under the curve x squared from 0 to 1 plus the area under g of x from 1 to 2. So if we go horizontally, we're going to need more than one integral. However, if we switch this time and look at horizontal rectangles and integrate vertically with respect to y, we only need one integral. The leftmost curve is going to be f of x, so that's the one we're going to subtract. The rightmost curve is going to be g of x, so that's the one we're going to start with. And so it's already clearly marked for us, so we know we want the integral from 0 to 1. Again, we're going vertically. And so the curve all the way to the right is going to be g of x minus the curve that is more to the left, which is f of x. That actually will not work. Sorry, I misspoke. We're getting close, but these functions, I know this because of the way I wrote the variables down incorrectly. These functions are f of x. If we want to go with respect to y, then we need to solve these for y. So in this case, x would be equal to the square root of y. The positive side is going to be the right side of the curve, which is the one we want. We should get a plus or minus, but we don't need the negative side of the graph. So the positive side is all we need. And then this one would be x equals 2 minus y when we reorganize that. Now we can do what we were saying. The integral from 0 to 1, the curve that is on the right is 2 minus y minus the curve that is on the left, which is the square root of y, or y to the 1/2, and we want our integral to be dy because we're going vertically. And so again, I don't want to spend time on this video on integration, so let's put that in our calculator and see what we get. So using my calculator, I get about 0.833. that one won't convert to a fraction for me. So this is an example of where using horizontal rectangles instead of vertical can actually save us some work. So the last thing that is on here is a couple of free response questions, or just one. I'm going to go ahead and leave this one for you to try yourself, and you can check the answer that's posted on the PDF. This one is number 5, which means it would be a no calculator question. Okay, so that is something to keep in mind as you are trying this on your own. So go ahead and give yourself a minute to try this one on your own. You can go to Canvas and check the work on the PDF, and I will see you all later.